Measurement and scaling techniques 69. 5 Measurement and scaling techniques. Measurement in research. In our daily life we are said to measure when we use some yardstick to determine weight, height, or some other feature of a physical object. We also measure when we judge how well we like a song, a painting, or the personalities of our friends. We, thus, measure physical objects as well as abstract concepts. Measurement is a relatively complex and demanding task, especially so when it concerns qualitative or abstract phenomena. By measurement we mean the process of assigning numbers to objects or observations, the level of measurement being a function of the rules under which the numbers are assigned. It is easy to assign numbers in respect of properties of some objects, but it is relatively difficult in respect of others. For instance, measuring such things as social conformity, intelligence, or marital adjustment is much less obvious and requires much closer attention than measuring physical weight, biological age, or a person's financial assets. In other words, properties like weight, height, etc., can be measured directly with some standard unit of measurement, but it is not that easy to measure properties like motivation to succeed, ability to stand stress, and the like. We can expect high accuracy in measuring the length of pipe with a yardstick, but if the concept is abstract and the measurement tools are not standardized, we are less confident about the accuracy of the results of measurement. Technically speaking, measurement is a process of mapping aspects of a domain onto other aspects of a range according to some rule of correspondence. In measuring, we devise some form of scale in the range. In terms of set theory, range may refer to some set and then transform or map the properties of objects from the domain. In terms of set theory, domain may refer to some other set onto this scale. For example, in case we are to find the male to female attendance ratio while conducting a study of persons who attend some show, then we may tabulate those who come to the show according to sex. In terms of set theory, this process is one of mapping the observed physical properties of those coming to the show, the domain, onto a sex classification, the range. The rule of correspondence is, if the object in the domain appears to be male, assign to 0, and if female, assign to 1. Similarly, we can record a person's marital status as 1, 2, 3, or 4, depending on whether. 70 Research methodology. The person is single, married, widowed, or divorced. We can as well record yes or no answers to a question as 0 and 1, or as 1 and 2, or perhaps as 59 and 60. In this artificial or nominal way, categorical data, qualitative or descriptive, can be made into numerical data, and if we thus code the various categories, we refer to the numbers we record as nominal data. Nominal data are numerical in name only, because they do not share any of the properties of the numbers we deal in ordinary arithmetic. For instance, if we record marital status as 1, 2, 3, or 4 as stated above, we cannot write 4 greater than 2 or 3 less than 4, and we cannot write 3 to 1 equals 4 to 2, 1 plus 3 equals 4, or 4 divided by 2 equals 2. In those situations when we cannot do anything except set up inequalities, we refer to the data as ordinal data. For instance, if one mineral can scratch another, it receives a higher hardness number, and on Mohs scale the numbers from 1 to 10 are assigned respectively to talc, gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, sapphire, and diamond. With these numbers we can write 5 greater than 2 or 6 less than 9, as apatite is harder than gypsum and feldspar is softer than sapphire, but we cannot write, for example, 10 to 9 equals 5 to 4, because the difference in hardness between diamond and sapphire is actually much greater than that between apatite and fluorite. It would also be meaningless to say that topaz is twice as hard as fluorite simply because their respective hardness numbers on Mohs scale are 8 and 4. The greater than symbol, i.e., greater than, in connection with ordinal data may be used to designate happier than, preferred to, and so on. When in addition to setting up inequalities we can also form differences, we refer to the data as interval data. Suppose we are given the following temperature readings in degrees Fahrenheit: 58 degrees, 63 degrees, 70 degrees, 95 degrees, 110 degrees, 126 degrees, and 135 degrees. In this case, we can write 100 degrees greater than 70 degree or 95 degrees less than 135 degrees, which simply means that 110 degrees is warmer than 70 degrees and that 95 degrees is cooler than 135 degrees. We can also write, for example, 95 degrees 70 degrees equals 135 degree 110 degrees, since equal temperature differences are equal in the sense that the same amount of heat is required to raise the temperature of an object from 70 degrees to 95 degrees or from 110 degrees to 135 degrees. On the other hand, it would not mean much if we said that 126 degrees is twice as hot as 63 degrees, even. Though 126 degrees divided by 63 degrees equals 2. To show the reason, we have only to change to the centigrade scale, where the first temperature becomes 5/9, 126 to 32 equals 52 degrees, the second temperature becomes 5/9, 63/32 equals 17 degrees, and the first figure is now more than 3 times the second. This difficulty arises from the fact that Fahrenheit and centigrade scales both have artificial origins, zeros, i.e., the number 0 of neither scale is indicative of the absence of whatever quantity we are trying to measure. When in addition to setting up inequalities and forming differences we can also form quotients, i.e., when we can perform all the customary operations of mathematics, we refer to such data as ratio data. In this sense, ratio data includes all the usual measurement, or determinations, of length, height, money amounts, weight, volume, area, pressures, etc. The above stated distinction between nominal, ordinal, interval and ratio data is important, for the nature of a set of data may suggest the use of particular statistical techniques. A researcher has to be quite alert about this aspect while measuring properties of objects or of abstract concepts. When data can be measured in units which are interchangeable, e.g., weights by ratio scales, temperatures by interval scales, that data is said to be parametric and can be subjected to most kinds of statistical and mathematical processes. But when data is measured in units which are not interchangeable, e.g., product preferences by ordinal scales, the data is said to be non-parametric and is susceptible only to a limited extent to mathematical and statistical treatment. Measurement and scaling techniques. 71 Measurement scales. From what has been stated above, we can write that scales of measurement can be considered in terms of their mathematical properties. The most widely used classification of measurement scales are A. Nominal scale, B. Ordinal scale, C. Interval scale, and D. Ratio scale. A. Nominal scale. Nominal scale is simply a system of assigning number symbols to events in order to label them. The usual example of this is the assignment of numbers of basketball players in order to identify them. Such numbers cannot be considered to be associated with an ordered scale, for their order is of no consequence. The numbers are just convenient labels for the particular class of events and as such have no quantitative value. Nominal scales provide convenient ways of keeping track of people, objects and events. One cannot do much with the numbers involved. For example, one cannot usefully average the numbers on the back of a group of football players and come up with a meaningful value. Neither can one usefully compare the numbers assigned to one group with the numbers assigned to another. The counting of members in each group is the only possible arithmetic operation when a nominal scale is employed. Accordingly, we are restricted to use mode as the measure of central tendency. There is no generally used measure of dispersion for nominal scales. Chi-square test is the most common test of statistical significance that can be utilized, and for the measures of correlation, the contingency coefficient can be worked out. Nominal scale is the least powerful level of measurement. It indicates no order or distance relationship and has no arithmetic origin. A nominal scale simply describes differences between things by assigning them to categories. Nominal data are, thus, counted data. The scale wastes any information that we may have about varying degrees of attitude, skills, understandings, etc. In spite of all this, nominal scales are still very useful and are widely used in surveys and other ex post facto research when data are being classified by major subgroups of the population. B. Ordinal scale. The lowest level of the ordered scale that is commonly used is the ordinal scale. The ordinal scale places events in order, but there is no attempt to make the intervals of the scale equal in terms of some rule. Rank orders represent ordinal scales and are frequently used in research relating to qualitative phenomena. A student's rank in his graduation class involves the use of an ordinal scale. One has to be very careful in making statement about scores based on ordinal scales. For instance, if Ram's position in his class is 10 and Mohan's position is 40, it cannot be said that Ram's position is 4 times as good as that of Mohan. The statement would make no sense at all. Ordinal scales only permit the ranking of items from highest to lowest. Ordinal measures have no absolute values, and the real differences between adjacent ranks may not be equal. All that can be said is that one person is higher or lower on the scale than another, but more precise comparisons cannot be made. Thus, the use of an ordinal scale implies a statement of greater than, or less than. An equality statement is also acceptable without our being able to state how much greater or less. The real difference between ranks 1 and the second of may be more or less than the difference between ranks 5 and 6. Since the numbers of this scale have only a rank meaning, the appropriate measure of central tendency is the median. A percentile or quartile measure is used for measuring dispersion. Correlations are restricted to various rank order methods. Measures of statistical significance are restricted to the non-parametric methods. See interval scale. In the case of interval scale, the intervals are adjusted in terms of some rule that has been established as a basis for making the units equal. The units are equal only insofar as 1.72 research methodology accepts the assumptions on which the rule is based. Interval scales can have an arbitrary zero, but it is not possible to determine for them what may be called an absolute zero or the unique origin. The primary limitation of the interval scale is the lack of a true zero. It does not have the capacity to measure the complete absence of a trait or characteristic. The Fahrenheit scale is an example of an interval scale and shows similarities in what one can and cannot do with it. One can say that an increase in temperature from 30 degrees to 40 degrees involves the same increase in temperature as an increase from 60 degrees to 70 degrees, but one cannot say that the temperature of 60 degrees is twice as warm as the temperature of 30 degrees because both numbers are dependent on the fact that the zero on the scale is set arbitrarily at the temperature of the freezing point of water. The ratio of the two temperatures, 30 degrees and 60 degrees, means nothing because zero is an arbitrary point. Interval scales provide more powerful measurement than ordinal scales, for interval scale also incorporates the concept of equality of interval. As such, more powerful statistical measures can be used with interval scales. Mean is the appropriate measure of central tendency, while standard deviation is the most widely used measure of dispersion. Product moment correlation techniques are appropriate, and the generally used tests for statistical significance are the t-test and f-test. D-ratio scale. Ratio scales have an absolute or true zero of measurement. The term, absolute zero, is not as precise as it was once believed to be. We can conceive of an absolute zero of length, and similarly we can conceive of an absolute zero of time. For example, the 0 point on a centimeter scale indicates the complete absence of length or height. But an absolute zero of temperature is theoretically unobtainable, and it remains a concept existing only in the scientist's mind. The number of minor traffic rule violations and the number of incorrect letters in a page of TypeScript represent scores on ratio scales. Both these scales have absolute zeros, and as such all minor traffic violations and all typing errors can be assumed to be equal in significance. With ratio scales involved, one can make statements like, Jyoti's typing performance was twice as good as that of Ritu. The ratio involved does have significance and facilitates a kind of comparison which is not possible in case of an interval scale. Ratio scale represents the actual amounts of variables. Measures of physical dimensions such as weight, height, distance, etc. are examples. Generally, all statistical techniques are usable with ratio scales, and all manipulations that one can carry out with real numbers can also be carried out with ratio scale values. Multiplication and division can be used with this scale but not with other scales mentioned above. Geometric and harmonic means can be used as measures of central tendency, and coefficients of variation may also be calculated. Thus, proceeding from the nominal scale, the least precise type of scale, to ratio scale, the most precise relevant information is obtained increasingly. If the nature of the variables permits, the researcher should use the scale that provides the most precise description. Researchers in physical sciences have the advantage to describe variables in ratio scale form, but the behavioral sciences are generally limited to describe variables in interval scale form, a less precise type of measurement. Sources of error in measurement should be precise and unambiguous in an ideal research study. This objective, however, is often not met with an entirety. As such, the researcher must be aware about the sources of error in measurement. The following are the possible sources of error in measurement. Measurement and scaling techniques. 73. A respondent. At times the respondent may be reluctant to express strong negative feelings, or it is just possible that he may have very little knowledge but may not admit his ignorance. All this reluctance is likely to result in an interview of guesses. Transient factors like fatigue, boredom, anxiety, etc. may limit the ability of the respondent to respond accurately and fully. B. Situation. Situational factors may also come in the way of correct measurement. Any condition which places a strain on interview can have serious effects on the interviewer-respondent rapport. For instance, if someone else is present, he can distort responses by joining in or merely by being present. If the respondent feels that anonymity is not assured, he may be reluctant to express certain feelings. C. Measurer. The interviewer can distort responses by rewording or reordering questions. His behavior, style and looks may encourage or discourage certain replies from respondents. Careless mechanical processing may distort the findings. Errors may also creep in because of incorrect coding, faulty tabulation and/or statistical calculations, particularly in the data analysis stage. D. Instrument. Error may arise because of the defective measuring instrument. The use of complex words, beyond the comprehension of the respondent, ambiguous meanings, poor printing, inadequate space for replies, response choice omissions, etc. are a few things that make the measuring instrument defective and may result in measurement errors. Another type of instrument deficiency is the poor sampling of the universe of items of concern. Researcher must know that correct measurement depends on successfully meeting all of the problems listed above. He must, to the extent possible, try to eliminate, neutralize or otherwise deal with all the possible sources of error so that the final results may not be contaminated. Tests of sound measurement. Sound measurement must meet the tests of validity, reliability and practicality. In fact, these are the three major considerations one should use in evaluating a measurement tool. Validity refers to the extent to which a test measures what we actually wish to measure. Reliability has to do with the accuracy and precision of a measurement procedure. Practicality is concerned with a wide range of factors of economy, convenience, and interpretability. We briefly take up the relevant details concerning these tests of sound measurement. 1. Test of validity. Validity is the most critical criterion and indicates the degree to which an instrument measures what it is supposed to measure. Validity can also be thought of as utility. In other words, validity is the extent to which differences found with a measuring instrument reflect true differences among those being tested. But the question arises, how can one determine validity without direct confirming knowledge? The answer may be that we seek other relevant evidence that confirms the answers we have found with our measuring tool. What is relevant? Evidence often depends upon the nature of the 1. Robert L. Thorndike and Elizabeth Hagen, Measurement and Evaluation in Psychology and Education, 3rd ed., p. 162. Two forms of validity are usually mentioned in research literature, viz. the external validity and the internal validity. External validity of research findings is their generalizability to populations, settings, treatment variables and measurement variables. We shall talk about it in the context of significance tests later on. The internal validity of a research design is its ability to measure what it aims to measure. We shall deal with this validity only in the present chapter. 74. Research methodology. Research problem and the judgment of the researcher. But one can certainly consider three types of validity in this connection: I. Content validity, E. Criterion-related validity and E. Construct validity. I. Content validity is the extent to which a measuring instrument provides adequate coverage of the topic under study. If the instrument contains a representative sample of the universe, the content validity is good. Its determination is primarily judgmental and intuitive. It can also be determined by using a panel of persons who shall judge how well the measuring instrument meets the standards, but there is no numerical way to express it. E. Criterion-related validity relates to our ability to predict some outcome or estimate the existence of some current condition. This form of validity reflects the success of measures used for some empirical estimating purpose. The concerned criterion must possess the following qualities. Relevance. A criterion is relevant if it is defined in terms we judge to be the proper measure. Freedom from bias. Freedom from bias is attained when the criterion gives each subject an equal opportunity to score well. Reliability. A reliable criterion is stable or reproducible. Availability. The information specified by the criterion must be available. In fact, a criterion-related validity is a broad term that actually refers to I. Predictive validity and E. Concurrent validity. The former refers to the usefulness of a test in predicting some future performance, whereas the latter refers to the usefulness of a test in closely relating to other measures of known validity. Criterion-related validity is expressed as the coefficient of correlation between test scores and some measure of future performance, or between test scores and scores on another measure of known validity. E. Construct validity is the most complex and abstract. A measure is said to possess construct validity to the degree that it confirms to predicted correlations with other theoretical propositions. Construct validity is the degree to which scores on a test can be accounted for by the explanatory constructs of a sound theory. For determining construct validity, we associate a set of other propositions with the results received from using our measurement instrument. If measurements on our devised scale correlate in a predicted way with these other propositions, we can conclude that there is some construct validity. If the above stated criteria and tests are met with, we may state that our measuring instrument is valid and will result in correct measurement, otherwise we shall have to look for more information and/or resort to exercise of judgment. 2. Test of reliability. The test of reliability is another important test of sound measurement. A measuring instrument is reliable if it provides consistent results. Reliable measuring instrument does contribute to validity, but a reliable instrument need not be a valid instrument. For instance, a scale that consistently overweighs objects by 5 kgs is a reliable scale, but it does not give a valid measure of weight. But the other way is not true, i.e., a valid instrument is always reliable. Accordingly, reliability is not as valuable as validity, but it is easier to assess reliability in comparison to validity. If the quality of reliability is satisfied by an instrument, then while using it we can be confident that the transient and situational factors are not interfering. Measurement and scaling techniques 75. Two aspects of reliability, viz. Stability and equivalence, deserve special mention. The stability aspect is concerned with securing consistent results with repeated measurements of the same person and with the same instrument. We usually determine the degree of stability by comparing the results of repeated measurements. The equivalence aspect considers how much error may get introduced by different investigators or different samples of the items being studied. A good way to test for the equivalence of measurements by two investigators is to compare their observations of the same events. Reliability can be improved in the following two ways. By standardizing the conditions under which the measurement takes place, i.e., we must ensure that external sources of variation such as boredom, fatigue, etc., are minimized to the extent possible. That will improve stability aspect. By carefully designed directions for measurement with no variation from group to group, by using trained and motivated persons to conduct the research, and also by broadening the sample of items used. This will improve equivalence aspect. 3. Test of practicality. The practicality characteristic of a measuring instrument can be judged in terms of economy, convenience and interpretability. From the operational point of view, the measuring instrument ought to be practical, i.e., it should be economical, convenient and interpretable. Economy consideration suggests that some trade-off is needed between the ideal research project and that which the budget can afford. The length of measuring instrument is an important area where economic pressures are quickly felt. Although more items give greater reliability as stated earlier, but in the interest of limiting the interview or observation time, we have to take only few items for our study purpose. Similarly, data collection methods to be used are also dependent at times upon economic factors. Convenience test suggests that the measuring instrument should be easy to administer. For this purpose one should give due attention to the proper layout of the measuring instrument. For instance, a questionnaire, with clear instructions illustrated by examples, is certainly more effective and easier to complete than one which lacks these features. Interpretability consideration is especially important when persons other than the designers of the test are to interpret the results. The measuring instrument, in order to be interpretable, must be supplemented by A. Detailed instructions for administering the test, B. Scoring keys, C. Evidence about the reliability, and D. Guides for using the test and for interpreting results. Technique of developing measurement tools. The technique of developing measurement tools involves a four-stage process, consisting of the following: A. Concept development, B. Specification of concept dimensions, C. Selection of indicators, and D. Formation of index. The first and foremost step is that of concept development, which means that the researcher should arrive at an understanding of the major concepts pertaining to his study. This step of concept 76 research methodology. Development is more apparent in theoretical studies than in the more pragmatic research, where the fundamental concepts are often already established. The second step requires the researcher to specify the dimensions of the concepts that he developed in the first stage. This task may either be accomplished by deduction, i.e., by adopting a more or less intuitive approach, or by empirical correlation of the individual dimensions with the total concept and/or the other concepts. For instance, one may think of several dimensions such as product reputation, customer treatment, corporate leadership, concern for individuals, sense of social responsibility and so forth when one is thinking about the image of a certain company. Once the dimensions of a concept have been specified, the researcher must develop indicators for measuring each concept element. Indicators are specific questions, scales, or other devices by which respondents' knowledge, opinion, expectation, etc., are measured. As there is seldom a perfect measure of a concept, the researcher should consider several alternatives for the purpose. The use of more than one indicator gives stability to the scores and it also improves their validity. The last step is that of combining the various indicators into an index, i.e., formation of an index. When we have several dimensions of a concept or different measurements of a dimension, we may need to combine them into a single index. One simple way for getting an overall index is to provide scale values to the responses and then sum up the corresponding scores. Such an overall index would provide a better measurement tool than a single indicator because of the fact that an individual indicator has only a probability relation to what we really want to know. To this way we must obtain an overall index for the various concepts concerning the research study. Scaling. In research we quite often face measurement problem since we want a valid measurement but may not obtain it, especially when the concepts to be measured are complex and abstract and we do not possess the standardized measurement tools. Alternatively, we can say that while measuring attitudes and opinions, we face the problem of their valid measurement. Similar problem may be faced by a researcher, of course in a lesser degree, while measuring physical or institutional concepts. As such we should study some procedures which may enable us to measure abstract concepts more accurately. This brings us to the study of scaling techniques. Meaning of scaling. Scaling describes the procedures of assigning numbers to various degrees of opinion, attitude and other concepts. This can be done in two ways, viz. Making a judgment about some characteristic of an individual and then placing him directly on a scale that has been defined in terms of that characteristic, and constructing questionnaires in such a way that the score of individual's responses assigns him a place on a scale. It may be stated here that a scale is a continuum, consisting of the highest point in terms of some characteristic, e.g., preference, favorableness, etc., and the lowest point along with several intermediate points between these two extreme points. These scale point positions are so related to each other that when the first point happens to be the highest point, the second point indicates a higher degree in terms of a given characteristic as compared to the third two. Lasersfeld, Evidence and Inference, p. 112. Measurement and Scaling Techniques 77 point, and the third point indicates a higher degree as compared to the fourth, and so on. Numbers for measuring the distinctions of degree in the attitudes, opinions are, thus, assigned to individuals corresponding to their scale positions. All this is better understood when we talk about scaling techniques. Hence the term, scaling, is applied to the procedures for attempting to determine quantitative measures of subjective abstract concepts. Scaling has been defined as a procedure for the assignment of numbers or other symbols to a property of objects in order to impart some of the characteristics of numbers to the properties in question. 3 Scale classification bases. The number assigning procedures or the scaling procedures may be broadly classified on one or more of the following bases: A. Subject orientation, B. Response form, C. Degree of subjectivity, D. Scale properties, E. Number of dimensions, and F. Scale construction techniques. We take up each of these separately. A. Subject orientation. Under it a scale may be designed to measure characteristics of the respondent who completes it or to judge the stimulus object which is presented to the respondent. In respect of the former, we presume that the stimuli presented are sufficiently homogeneous so that the between stimuli variation is small as compared to the variation among respondents. In the latter approach, we ask the respondent to judge some specific object in terms of one or more dimensions, and we presume that the between respondent variation will be small as compared to the variation among the different stimuli presented to respondents for judging. B. Response form. Under this we may classify the scales as categorical and comparative. Categorical scales are also known as rating scales. These scales are used when a respondent scores some object without direct reference to other objects. Under comparative scales, which are also known as ranking scales, the respondent is asked to compare 2 or more objects. In this sense the respondent may state that one object is superior to the other, or that 3 models of pen rank in order 1, 2 and 3. The essence of ranking is, in fact, a relative comparison of a certain property of 2 or more objects. C. Degree of subjectivity. With this basis the scale data may be based on whether we measure subjective personal preferences or simply make non-preference judgments. In the former case, the respondent is asked to choose which person he favors or which solution he would like to see employed, whereas in the latter case he is simply asked to judge which person is more effective in some aspect or which solution will take fewer resources without reflecting any personal preference. D. Scale properties. Considering scale properties, one may classify the scales as nominal, ordinal, interval and ratio scales. Nominal scales merely classify without indicating order, distance or unique origin. Ordinal scales indicate magnitude relationships of more than, or less than, but indicate no distance or unique origin. Interval scales have both order and distance values, but no unique origin. Ratio scales possess all these features. E. Number of dimensions. In respect of this basis, scales can be classified as unidimensional and multidimensional scales. Under the former we measure only one attribute of the respondent or object, whereas multidimensional scaling recognizes that an object might be described better by using the concept of an attribute space of n dimensions, rather than a single-dimension continuum. 3. Bernard S. Phillips, Social Research Strategy and Tactics, 2nd ed., p. 205. 78. Research Methodology F. Scale Construction Techniques. Following are the 5 main techniques by which scales can be developed. Arbitrary approach. It is an approach where scale is developed on ad hoc basis. This is the most widely used approach. It is presumed that such scales measure the concepts for which they have been designed, although there is little evidence to support such an assumption. Consensus approach. Here a panel of judges evaluate the items chosen for inclusion in the instrument in terms of whether they are relevant to the topic area and unambiguous in implication. Item analysis approach. Under it a number of individual items are developed into a test which is given to a group of respondents. After administering the test, the total scores are calculated for every one. Individual items are then analyzed to determine which items discriminate between persons or objects with high total scores and those with low scores. Cumulative scales are chosen on the basis of their conforming to some ranking of items with ascending and descending discriminating power. For instance, in such a scale the endorsement of an item representing an extreme position should also result in the endorsement of all items indicating a less extreme position. V-factor scales may be constructed on the basis of intercorrelations of items which indicate that a common factor accounts for the relationship between items. This relationship is typically measured through factor analysis method. Important scaling techniques. We now take up some of the important scaling techniques often used in the context of research, especially in context of social or business research. Rating scales. The rating scale involves qualitative description of a limited number of aspects of a thing or of traits of a person. When we use rating scales or categorical scales, we judge an object in absolute terms against some specified criteria, i.e., we judge properties of objects without reference to other similar objects. These ratings may be rating scale may be either a graphic rating scale or an itemized rating scale. Measurement and scaling techniques. 79. How do you like the product? Please check like, very much like, somewhat neutral. Fig. 5.1. Dislike, somewhat dislike, very much. This type of scale has several limitations. The respondents may check at almost any position along the line, which fact may increase the difficulty of analysis. The meanings of the terms like, very much, and somewhat may depend upon respondents' frame of reference so much so that the statement might be challenged in terms of its equivalency. Several other rating scale variants, e.g., boxes replacing line, may also be used. The itemized rating scale, also known as numerical scale, presents a series of statements from which a respondent selects one as best reflecting his evaluation. These statements are ordered progressively in terms of more or less of some property. An example of itemized scale can be given to illustrate it. Suppose we wish to inquire as to how well does a worker get along with his fellow workers. In such a situation we may ask the respondent to select one, to express his opinion, from the following: and he is almost always involved in some friction with a fellow worker, and he is often at odds with one or more of his fellow workers, and he sometimes gets involved in friction, and he infrequently becomes involved in friction with others, and he almost never gets involved in friction with fellow workers. The chief merit of this type of scale is that it provides more information and meaning to the rater, and thereby increases reliability. This form is relatively difficult to develop and the statements may not say exactly what the respondent would like to express. Rating scales have certain good points. The results obtained from their use compare favorably with alternative methods. They require less time, are interesting to use and have a wide range of applications. Besides, they may also be used with a large number of properties or variables. But their value for measurement purposes depends upon the assumption that the respondents can and do make good judgments. If the respondents are not very careful while rating, errors may occur. 3 types of errors are common, viz. the error of leniency, the error of central tendency, and the error of halo effect. The error of leniency occurs when certain respondents are either easy raters or hard raters. When raters are reluctant to give extreme judgments, the result is the error of central tendency. The error of halo effect or the systematic bias occurs when the rater carries over a generalized impression of the subject from one rating to another. This sort of error takes place when we conclude, for example, that a particular report is good because we like its form, or that someone is intelligent because he agrees with us or has a pleasing personality. In other words, halo effect is likely to appear when the rater is asked to rate many factors, on a number of which he has no evidence for judgment. 80 Research methodology ranking scales. Under ranking scales are comparative scales. We make relative judgments against other similar objects. The respondents under this method directly compare two or more objects and make choices among them. There are two generally used approaches of ranking scales, viz. A method of paired comparisons. Under it the respondent can express his attitude by making a choice between two objects, say between a new flavor of soft drink and an established brand of drink. But when there are more than two stimuli to judge, the number of judgments required in a paired comparison is given by the formula, n equals -1 bg2. Where n equals number of judgments, n equals number of stimuli or objects to be judged. For instance, if there are 10 suggestions for bargaining proposals available to a workers' union, there are 45 paired comparisons that can be made with them. When n happens to be a big figure, there is the risk of respondents giving ill-considered answers, or they may even refuse to answer. We can reduce the number of comparisons per respondent either by presenting to each one of them only a sample of stimuli or by choosing a few objects which cover the range of attractiveness at about equal intervals and then comparing all other stimuli to these few standard objects. Thus, paired comparison data may be treated in several ways. If there is substantial consistency, we will find that if X is preferred to Y, and Y to Z, then X will consistently be preferred to Z. If this is true, we may take the total number of preferences among the comparisons as the score for that stimulus. It should be remembered that paired comparison provides ordinal data, but the same may be converted into an interval scale by the method of the law of comparative judgment developed by L.L. Thurstone. This technique involves the conversion of frequencies of preferences into a table of proportions which are then transformed into Z matrix by referring to the table of area under the normal curve. J.P. Guilford in his book, Psychometric Methods, has given a procedure which is relatively easier. The method is known as the composite standard method and can be illustrated as under. Suppose there are 4 proposals which some union bargaining committee is considering. The committee wants to know how the union membership ranks these proposals. For this purpose a sample of 100 members might express the views as shown in the following table, Table 5.1. Response patterns of 100 members, paired comparisons of 4 suggestions for union bargaining proposal priorities. Suggestion A, B, C, D, A-65 *32 20 B 40 C, D 45 80 total 1655020 135 read as 65 members preferred. Suggestion B to suggestion A 3898 168 42 70 132 counted. Measurement and Scaling Techniques 81 Rank Order 2314 MP 0.5375 0.4625 0.5450 0.4550 ZJ 0.09 0.090 0.11 0.11 RJ 0.20 0.020 0.22 0.00 Comparing the total number of preferences for each of the 4 proposals, we find that C is the most popular, followed by A, B and D respectively in popularity. The rank order shown in the above table explains all this. By following the composite standard method, we can develop an interval scale from the paired comparison ordinal data given in the above table, for which purpose we have to adopt the following steps in order. Using the data in the above table, we work out the column mean with the help of the formula given below. MCNNNP equals 516551004 4100 5375 BG where MP equals the mean proportion of the columns, C equals the total number of choices for a given suggestion, N equals number of stimuli proposals in the given problem, N equals number of items in the sample. The column means have been shown in the MP row in the above table. The Z values for the MP are secured from the table giving the area under the normal curve. When the MP value is less than 0.5, the Z value is negative, and for all MP values higher than 0.5, the Z values are positive. These Z values are shown in ZJ row in the above table. As the ZJ values represent an interval scale, 0 is an arbitrary value. Hence we can eliminate negative scale values by giving the value of 0 to the lowest scale value, this being 0.11 in our example, which we shall take equal to 0, and then adding the absolute value of this lowest scale value to all other scale items. This scale has been shown in RJ row in the above table. Graphically we can show this interval scale that we have derived from the paired comparison data using the composite standard method as follows. Fig. 5.2 * to use normal curve area table for this sort of transformation, we must subtract 0.5 from all MP values which exceed 0.5 to secure the values with which to enter the normal curve area table for which Z values can be obtained. For all MP values of less than 5. We must subtract all such values from 0.5 to secure the values with which to enter the normal curve area table for which z-values can be obtained, but the z-values in this situation will be with negative sign. 0.0, 0.1, 0.2, 0.3, 0.4 dBAC. 82. Research methodology. B. Method of rank order. Under this method of comparative scaling, the respondents are asked to rank their choices. This method is easier and faster than the method of paired comparisons stated above. For example, with 10 items it takes 45 pair comparisons to complete the task, whereas the method of rank order simply requires ranking of 10 items only. The problem of transitivity, such as A prefers to B, B to C, but C prefers to A, is also not there in case we adopt method of rank order. Moreover, a complete ranking at times is not needed, in which case the respondents may be asked to rank only their first, say, 4 choices, while the number of overall items involved may be more than 4, say, it may be 15 or 20 or more. To secure a simple ranking of all items involved, we simply total rank values received by each item. There are methods through which we can as well develop an interval scale of these data. But then there are limitations of this method. The first one is that data obtained through this method are ordinal data, and hence rank ordering is an ordinal scale with all its limitations. Then there may be the problem of respondents becoming careless in assigning ranks, particularly when there are many, usually more than 10, items. Scale construction techniques in social science studies. While measuring attitudes of the people, we generally follow the technique of preparing the opinionaire asterisk, or attitude scale, in such a way that the score of the individual responses assigns him a place on a scale. Under this approach, the respondent expresses his agreement or disagreement with a number of statements relevant to the issue. While developing such statements, the researcher must note the following 2 points. That the statements must elicit responses which are psychologically related to the attitude being measured. That the statements need be such that they discriminate not merely between extremes of attitude but also among individuals who differ slightly. Researchers must as well be aware that inferring attitude from what has been recorded in opinionaires has several limitations. People may conceal their attitudes and express socially acceptable opinions. They may not really know how they feel about a social issue. People may be unaware of their attitude about an abstract situation. Until confronted with a real situation, they may be unable to predict their reaction. Even behavior itself is at times not a true indication of attitude. For instance, when politicians kiss babies, their behavior may not be a true expression of affection toward infants. Thus, there is no sure method of measuring attitude. We only try to measure the expressed opinion and then draw inferences from it about people's real feelings or attitudes. With all these limitations in mind, psychologists and sociologists have developed several scale construction techniques for the purpose. The researcher should know these techniques so as to develop an appropriate scale for his own study. Some of the important approaches, along with the corresponding scales developed under each approach to measure attitude, are as follows. An information form that attempts to measure the attitude or belief of an individual is known as opinionaire. Measurement and scaling techniques. 83. Table 5.2. Different scales for measuring attitudes of people. Name of the scale construction approach. 1. Arbitrary approach. 2. Consensus scale approach. 3. Item analysis approach. 4. Cumulative scale approach. 5. Factor analysis approach. Name of the scale developed. Arbitrary scales. Differential scales, such as Thurstone differential scale. Summated scales, such as Likert scale. Cumulative scales, such as Gutmann's scalegram. Factor scales, such as Osgood's semantic differential, multi-dimensional scaling, etc. A brief description of each of the above listed scales will be helpful. Arbitrary scales. Arbitrary scales are developed on ad hoc basis and are designed largely through the researcher's own subjective selection of items. The researcher first collects few statements or items which he believes are unambiguous and appropriate to a given topic. Some of these are selected for inclusion in the measuring instrument, and then people are asked to check in a list the statements with which they agree. The chief merit of such scales is that they can be developed very easily, quickly, and with relatively less expense. They can also be designed to be highly specific and adequate. Because of these benefits, such scales are widely used in practice. At the same time, there are some limitations of these scales. The most important one is that we do not have objective evidence that such scales measure the concepts for which they have been developed. We have simply to rely on researchers' insight and competence. Differential scales are Thurstone-type scales. The name of L.L. Thurstone is associated with differential scales which have been developed using consensus scale approach. Under such an approach, the selection of items is made by a panel of judges who evaluate the items in terms of whether they are relevant to the topic area and unambiguous in implication. The detailed procedure is as under. A. The researcher gathers a large number of statements, usually 20 or more, that express various points of view toward a group, institution, idea, or practice, i.e., statements belonging to the topic area. B. These statements are then submitted to a panel of judges, each of whom arranges them in 11 groups or piles ranging from one extreme to another in position. Each of the judges is requested to place generally in the first pile the statements which he thinks are most unfavorable to the issue, in the second pile to place those statements which he thinks are next most unfavorable, and he goes on doing so in this manner till in the 11th pile he puts the statements which he considers to be the most favorable. See, this sorting by each judge yields a composite position for each of the items. In case of marked disagreement between the judges in assigning a position to an item, that item is discarded. 84 Research methodology. D. For items that are retained, each is given its median scale value between 1 and 11 as established by the panel. In other words, the scale value of any one statement is computed as the median position to which it is assigned by the group of judges. A final selection of statements is then made. For this purpose, a sample of statements, whose median scores are spread evenly from one extreme to the other, is taken. The statements so selected constitute the final scale to be administered to respondents. The position of each statement on the scale is the same as determined by the judges. After developing the scale as stated above, the respondents are asked during the administration of the scale to check the statements with which they agree. The median value of the statements that they check is worked out, and this establishes their score or quantifies their opinion. It may be noted that in the actual instrument the statements are arranged in random order of scale value. If the values are valid and if the opinionaire deals with only one attitude dimension, the typical respondent will choose one or several contiguous items in terms of scale values to reflect his views. However, at times divergence may occur when a statement appears to tap a different attitude dimension. The Thurstone method has been widely used for developing differential scales which are utilized to measure attitudes towards varied issues like war, religion, etc. Such scales are considered most appropriate and reliable when used for measuring a single attitude. But an important deterrent to their use is the cost and effort required to develop them. Another weakness of such scales is that the values assigned to various statements by the judges may reflect their own attitudes. The method is not completely objective. It involves ultimately subjective decision process. Critics of this method also opine that some other scale designs give more information about the respondent's attitude in comparison to differential scales. Summated scales are Likert-type scales. Summated scales or Likert-type scales are developed by utilizing the item analysis approach, wherein a particular item is evaluated on the basis of how well it discriminates between those persons whose total score is high and those whose score is low. Those items or statements that best meet this sort of discrimination test are included in the final instrument. Thus, summated scales consist of a number of statements which express either a favorable or unfavorable attitude towards the given object to which the respondent is asked to react. The respondent indicates his agreement or disagreement with each statement in the instrument. Each response is given a numerical score, indicating its favorableness or unfavorableness, and the scores are totaled to measure the respondent's attitude. In other words, the overall score represents the respondent's position on the continuum of favorable-unfavorableness towards an issue. Most frequently used summated scales in the study of social attitudes follow the pattern devised by Likert. For this reason they are often referred to as Likert-type scales. In a Likert scale, the respondent is asked to respond to each of the statements in terms of several degrees, usually 5 degrees, but at times 3 or the 7th of may also be used, of agreement or disagreement. For example, when asked to express opinion whether one considers his job quite pleasant, the respondent may respond in any one of the following ways: I strongly agree, E undecided, IV disagree, V strongly disagree. Measurement and scaling techniques. 85 We find that these 5 points constitute the scale. At one extreme of the scale there is strong agreement with the given statement, and at the other, strong disagreement, and between them lie intermediate points. We may illustrate this as under: strongly agree 1, agree 2, undecided 3, fig. 5.3 disagree 4, strongly disagree 5. Each point on the scale carries a score. Response indicating the least favorable degree of job satisfaction is given the least score, say 1, and the most favorable is given the highest score, say 5. These score values are normally not printed on the instrument but are shown here just to indicate the scoring pattern. The Likert scaling technique, thus, assigns a scale value to each of the 5 responses. The same thing is done in respect of each and every statement in the instrument. This way the instrument yields a total score for each respondent, which would then measure the respondent's favorableness toward the given point of view. If the instrument consists of, say 30 statements, the following score values would be revealing. 30 times 5 equals 150 most favorable response possible, 30 times 3 equals 90 a neutral attitude, 30 times 1 equals 30 most unfavorable attitude. The scores for any individual would fall between 30 and 150. If the score happens to be above 90, it shows favorable opinion to the given point of view. A score of below 90 would mean unfavorable opinion, and a score of exactly 90 would be suggestive of a neutral attitude. Procedure. The procedure for developing a Likert type scale is as follows. As a first step, the researcher collects a large number of statements which are relevant to the attitude being studied, and each of the statements expresses definite favorableness or unfavorableness to a particular point of view or the attitude, and that the number of favorable and unfavorable statements is approximately equal. After the statements have been gathered, a trial test should be administered to a number of subjects. In other words, a small group of people, from those who are going to be studied finally, are asked to indicate their response to each statement by checking one of the categories of agreement or disagreement using a 5-point scale as stated above. The response to various statements are scored in such a way that a response indicative of the most favorable attitude is given the highest score of 5, and that with the most unfavorable attitude is given the lowest score, say, of 1. Then the total score of each respondent is obtained by adding his scores that he received for separate statements. The next step is to array these total scores and find out those statements which have a high discriminatory power. For this purpose, the researcher may select some part of the highest and the lowest total scores, say the top 25% and the bottom 25%. These two extreme groups are interpreted to represent the most favorable and the least favorable attitudes and are used as criterion groups by which to evaluate individual statements. This 86 research methodology way we determine which statements consistently correlate with low favorability and which with high favorability. Only those statements that correlate with the total test should be retained in the final instrument, and all others must be discarded from it. Advantages. The Likert type scale has several advantages. Mention may be made of the important ones. It is relatively easy to construct the Likert type scale in comparison to Thurstone type scale because Likert type scale can be performed without a panel of judges. Likert type scale is considered more reliable because under it respondents answer each statement included in the instrument. As such, it also provides more information and data than does the Thurstone type scale. Each statement, included in the Likert type scale, is given an empirical test for discriminating ability, and as such, unlike Thurstone type scale, the Likert type scale permits the use of statements that are not manifestly related to have a direct relationship to the attitude being studied. Likert type scale can easily be used in respondent-centered and stimulus-centered studies, i.e., through it we can study how responses differ between people and how responses differ between stimuli. Likert type scale takes much less time to construct. It is frequently used by the students of opinion research. Moreover, it has been reported in various research studies that there is high degree of correlation between Likert type scale and Thurstone type scale. Limitations. There are several limitations of the Likert type scale as well. One important limitation is that, with this scale, we can simply examine whether respondents are more or less favorable to a topic, but we cannot tell how much more or less they are. There is no basis for belief that the 5 positions indicated on the scale are equally spaced. The interval between strongly agree and agree may not be equal to the interval between agree and undecided. This means that Likert scale does not rise to a stature more than that of an ordinal scale, whereas the designers of Thurstone scale claim the Thurstone scale to be an interval scale. One further disadvantage is that often the total score of an individual respondent has little clear meaning, since a given total score can be secured by a variety of answer patterns. It is unlikely that the respondent can validly react to a short statement on a printed form in the absence of real-life qualifying situations. Moreover, there remains a possibility that people may answer according to what they think they should feel rather than how they do feel. For this particular weakness of the Likert type scale is met by using a cumulative scale, which we shall take up later in this chapter. In spite of all the limitations, the Likert type summated scales are regarded as the most useful in a situation wherein it is possible to compare the respondent's score with a distribution of scores from some well-defined group. They are equally useful when we are concerned with a program of A. L. Edwards and K.C. Kenny, A Comparison of the Thurstone and Likert Techniques of Attitude Scale Construction, Journal of Applied Psychology, 30, 72-83, 1946. 4 John W. Best and James V. Kahn, Research and Education, 5 ed. Prentice Hall of India Private. Limited, New Delhi, 1986, p. 183. Measurement and Scaling Techniques 87 Change or Improvement, in which case we can use the scales to measure attitudes before and after the program of change or improvement in order to assess whether our efforts have had the desired effects. We can as well correlate scores on the scale to other measures without any concern for the absolute value of what is favorable and what is unfavorable. All this accounts for the popularity of Likert-type scales in social studies relating to measuring of attitudes. Cumulative scales. Cumulative scales are Lewis Gutmann's scalegram analysis, like other scales, consist of series of statements to which a respondent expresses his agreement or disagreement. The special feature of this type of scale is that statements in it form a cumulative series. This, in other words, means that the statements are related to one another in such a way that an individual, who replies favorably to say item number 3, also replies favorably to items number 2 and 1, and one who replies favorably to item number 4 also replies favorably to items number 3, 2 and 1, and so on. This being so, an individual whose attitude is at a certain point in a cumulative scale will answer favorably all the items on one side of this point, and answer unfavorably all the items on the other side of this point. The individual's score is worked out by counting the number of points concerning the number of statements he answers favorably. If one knows this total score, one can estimate as to how a respondent has answered individual statements constituting cumulative scales. The major scale of this type of cumulative scales is the Gutmann scalegram. We attempt a brief description of the same below. The technique developed by Louis Gutmann is known as scalegram analysis, or at times simply, scale analysis. Scalegram analysis refers to the procedure for determining whether a set of items forms a unidimensional scale. A scale is said to be unidimensional if the responses fall into a pattern in which endorsement of the item reflecting the extreme position results also in endorsing all items which are less extreme. Under this technique, the respondents are asked to indicate in respect of each item whether they agree or disagree with it, and if these items form a unidimensional scale, the response pattern will be as under. Table 5.3, Response Pattern in Scalegram Analysis Item number 4321XXXX, XXX, XX Respondent Score 432, X equals agree equals disagree 10. A score of 4 means that the respondent is in agreement with all the statements, which is indicative of the most favorable attitude. But a score of 3 would mean that the respondent is not agreeable to item 4, but he agrees with all others. In the same way one can interpret other values of the respondent's scores. This pattern reveals that the universe of content is scalable. 88 Research Methodology Procedure. The procedure for developing a scalegram can be outlined as under. A. The universe of content must be defined first of all. In other words, we must lay down in clear terms the issue we want to deal with in our study. B. The next step is to develop a number of items relating the issue and to eliminate by inspection the items that are ambiguous, irrelevant, or those that happen to be too extreme items. C. The third step consists in pre-testing the items to determine whether the issue at hand is scalable. The pretest, as suggested by Gutmann, should include 12 or more items, while the final scale may have only 4 to 6 items. Similarly, the number of respondents in a pretest may be small, say 20 or 25, but final scale should involve relatively more respondents, say 100 or more. In a pretest, the respondents are asked to record their opinions on all selected items using a Likert type 5-point scale, ranging from strongly agree to strongly disagree. The strongest favorable response is scored as 5, whereas the strongest unfavorable response is 1. The total score can thus range, if there are 15 items in all, from 75 for most favorable to 15 for the least favorable. Respondent opinionaires are then arrayed according to total score for analysis and evaluation. If the responses of an item form a cumulative scale, its response category scores should decrease in an orderly fashion as indicated in the above table. Failure to show the said decreasing pattern means that there is overlapping, which shows that the item concerned is not a good cumulative scale item, i.e., the item has more than one meaning. Sometimes the overlapping in category responses can be reduced by combining categories. After analyzing the pretest results, a few items, say 5 items, may be chosen. The next step is again to total the scores for the various opinionaires, and to rearray them to reflect any shift in order, resulting from reducing the items, say, from 15 in pretest to, say, 5 for the final scale. The final pretest results may be tabulated in the form of a table given in Table 5.4. Table 5.4. The final pretest results in a scalogram analysis: scale type 5 perfect, 4 perfect, non-scale 3 perfect, 2 perfect, 1 perfect, non-scale 0 perfect. Item 5 1 2 3 errors 10 7 per case. Number of cases, number of errors XXXXXO 7 0XXXXO 3 0XXX1 1 1 XXX1 2 2 XXXO 5 0XXO 2 0 XO1 0X2 1 2 X2 1 2 020 N equals 5 N equals 25 E equals 7 asterisk. Figures in the table are arbitrary and have been used to explain the tabulation process only. Measurement and scaling techniques 89. The table shows that 5 items numbering 5, 12, 3, 10 and 7 have been selected for the final scale. The number of respondents is 25, whose responses to various items have been tabulated along with the number of errors. Perfect scale types are those in which the respondents' answers fit the pattern that would be reproduced by using the person's total score as a guide. Non-scale types are those in which the category pattern differs from that expected from the respondent's total score, i.e., non-scale cases have deviations from unidimensionality or errors. Whether the items or series of statements selected for final scale may be regarded a perfect cumulative or a unidimensional scale we have to examine on the basis of the coefficient of reproducibility. Gutmann has set 0.9 as the level of minimum reproducibility in order to say that the scale meets the test of unidimensionality. He has given the following formula for measuring the level of reproducibility. Gutmann's coefficient of reproducibility equals 1 E n n, WERI equals number of errors n equals number of items n equals number of cases for the above table figures. Coefficient of reproducibility equals 1 7/5 25 equals 0.94. This shows that items number 5, 12, 3, 10 and 7 in this order constitute the cumulative or unidimensional scale, and with this we can reproduce the responses to each item, knowing only the total score of the respondent concerned. Scalogram analysis, like any other scaling technique, has several advantages as well as limitations. One advantage is that it assures that only a single dimension of attitude is being measured. Researchers' subjective judgment is not allowed to creep in the development of scale, since the scale is determined by the replies of respondents. Then, we require only a small number of items that make such a scale easy to administer. Scalogram analysis can appropriately be used for personal, telephone or mail surveys. The main difficulty in using this scaling technique is that in practice perfect cumulative or unidimensional scales are very rarely found, and we have only to use its approximation, testing it through coefficient of reproducibility or examining it on the basis of some other criteria. This method is not a frequently used method for the simple reason that its development procedure is tedious and complex. Such scales hardly constitute a reliable basis for assessing attitudes of persons towards complex objects, for predicting the behavioral responses of individuals towards such objects. Conceptually, this analysis is a bit more difficult in comparison to other scaling methods. Factor scales. Factor scales are developed through factor analysis or on the basis of intercorrelations of items which indicate that a common factor accounts for the relationships between items. Factor scales are particularly useful in uncovering latent attitude dimensions and approach scaling through the concept of multiple dimension attribute space. 5. More specifically, the two problems viz. How to deal a detailed study of the factor scales and particularly the statistical procedures involved in developing factor scales is beyond the scope of this book. As such, only an introductory idea of factor scales is presented here. 5c. William Emery, Business Research Methods, p. 264-65. 90. Research methodology appropriately with the universe of content which is multidimensional, and how to uncover underlying, latent dimensions which have not been identified, are dealt with through factor scales. An important factor scale based on factor analysis is semantic differential, SD, and the other one is multidimensional scaling. We give below a brief account of these factor scales. Semantic differential scale. Semantic differential scale, or the SD scale, developed by Charles E. Osgood, G.J. Suki and P.H. Tannenbaum, 1957, is an attempt to measure the psychological meanings of an object to an individual. This scale is based on the presumption that an object can have different dimensions of connotative meanings which can be located in multidimensional property space, or what can be called the semantic space in the context of SD scale. This scaling consists of a set of bipolar rating scales, usually of 7 points, by which one or more respondents rate one or more concepts on each scale item. For instance, the SD scale items for analyzing candidates for leadership position may be shown as under: EAT successful P, severe P, heavy A, hot E, progressive P, strong A, active A, fast E, true E, sociable 3, 2, 1, 0, 1, 2, 3 Fig. 5.4 unsuccessful lenient light cold regressive weak passive. Slow false unsociable candidates for leadership position along with the concept, the ideal candidate may be compared and we may score them from +3 to -3 on the basis of the above stated scales. The letters E, P, A showing the relevant factor viz. Evaluation, potency and activity respectively, written along the left side are not written in actual scale. Similarly, the numeric values shown are also not written in actual scale. Osgood and others did produce a list of some adjective pairs for attitude research purposes and concluded that semantic space is multidimensional rather than unidimensional. They made sincere efforts and ultimately found that 3 factors, viz. Evaluation, potency and activity, contributed most to meaningful judgments by respondents. The evaluation dimension generally accounts for 1/2 and 3/4 of the extractable variance and the other 2 factors account for the balance. Procedure. Various steps involved in developing SD scale are as follows. A. First of all, the concepts to be studied are selected. The concepts are usually chosen by personal judgment, keeping in view the nature of the problem. Measurement and scaling techniques 91b. The next step is to select the scales bearing in mind the criterion of factor composition and the criterion of scales relevance to the concepts being judged. It is common practice to use at least 3 scales for each factor with the help of which an average factor score has to be worked out. One more criterion to be kept in view is that scales should be stable across subjects and concepts. See then a panel of judges are used to rate the various stimuli or objects on the various selected scales and the responses of all judges would then be combined to determine the composite scaling. To conclude, the SD has a number of specific advantages. It is an efficient and easy way to secure attitudes from a large sample. These attitudes may be measured in both direction and intensity. The total set of responses provides a comprehensive picture of the meaning of an object, as well as a measure of the subject doing the rating. It is a standardized technique that is easily repeated, but escapes many of the problems of response distortion found with more direct methods. 6. Multidimensional scaling. Multidimensional scaling (MDS) is relatively more complicated scaling device, but with this sort of scaling one can scale objects, individuals or both with a minimum of information. Multidimensional scaling, or MDS, can be characterized as a set of procedures for portraying perceptual or affective dimensions of substantive interest. It provides useful methodology for portraying subjective judgments of diverse kinds. 7. MDS is used when all the variables, whether metric or non-metric, in a study are to be analyzed simultaneously and all such variables happen to be independent. The underlying assumption in MDS is that respondents perceive a set of objects as being more or less similar to one another on a number of dimensions usually uncorrelated with one another instead of only one. 8. Through MDS techniques one can represent geometrically the locations and interrelationships among a set of points. In fact, these techniques attempt to locate the points, given the information about a set of interpoint distances, in space of one or more dimensions such as to best summarize the information contained in the interpoint distances. The distances in the solution space then optimally reflect the distances contained in the input data. For instance, if objects, say X and Y, are thought of by the respondent as being most similar as compared to all other possible pairs of objects, MDS techniques will position objects X and Y in such a way that the distance between them in multidimensional space is shorter than that between any 2 other objects. 2 approaches, viz. The metric approach and the non-metric approach, are usually talked about in the context of MDS, while attempting to construct a space containing M points such that M1, 2 interpoint distances reflect the input data. The metric approach to MDS treats the input data as interval scale data and solves applying statistical methods for the additive constant which 6 IBID, p. 260. 7 Paul E. Green, Analyzing Multivariate Data, p. 421. 8 Jagdish N. Sheth, The Multivariate Revolution in Marketing Research, quoted in Marketing Research, by Danny N. Bellinger and Barnett A. Greenberg, p. 255. Additive constant refers to that constant with which one can, either by subtracting or adding, convert interval scale to a ratio scale. For instance, suppose we know that distances, say A, B, C, C, D among stimuli on a ratio scale are 7, 6 and 3 respectively. If one were to subtract 3 from each of these distances, they would be 4, 3 and 0 respectively. The converted distances would be on an interval scale of measurement, but not on a ratio scale. Obviously, one can add 3 to all the converted distances and retrieve the ratio scale of distances. Thus 3 will be taken as the additive constant in this case. Well-defined iterative approach is employed in practice for estimating appropriate additive constant. 92 Research methodology minimizes the dimensionality of the solution space. This approach utilizes all the information in the data in obtaining a solution. The data, i.e., the metric similarities of the objects, are often obtained on a bipolar similarity scale on which pairs of objects are rated one at a time. If the data reflect exact distances between real objects in an r-dimensional space, their solution will reproduce the set of interpoint distances. But as the true and real data are rarely available, we require random and systematic procedures for obtaining a solution. Generally, the judged similarities among a set of objects are statistically transformed into distances by placing those objects in a multidimensional space of some dimensionality. The non-metric approach first gathers the non-metric similarities by asking respondents to rank order all possible pairs that can be obtained from a set of objects. Such non-metric data is then transformed into some arbitrary metric space and then the solution is obtained by reducing the dimensionality. In other words, this non-metric approach seeks a representation of points in a space of minimum dimensionality such that the rank order of the interpoint distances in the solution space maximally corresponds to that of the data. This is achieved by requiring only that the distances in the solution be monotone with the input data. 9. The non-metric approach has come into prominence during the 60s with the coming into existence of high-speed computers to generate metric solutions for ordinal input data. The significance of MDS lies in the fact that it enables the researcher to study the perceptual structure of a set of stimuli and the cognitive processes underlying the development of this structure. Psychologists, for example, employ multidimensional scaling techniques in an effort to scale psychophysical stimuli and to determine appropriate labels for the dimensions along which these stimuli vary. 10. The MDS techniques, in fact, do away with the need in the data collection process to specify the attributes along which the several brands, say of a particular product, may be compared, as ultimately the MDS analysis itself reveals such attributes that presumably underlie the expressed relative similarities among objects. Thus, MDS is an important tool in attitude measurement, and the techniques falling under MDS promise a great advance from a series of unidimensional measurements, e.g., a distribution of intensities of feeling towards single attributes such as color, taste or a preference ranking with indeterminate intervals, to a perceptual mapping in multidimensional space of objects, company images, advertisement brands, etc. 11. In spite of all the merits stated above, the MDS is not widely used because of the computation complications involved under it. Many of its methods are quite laborious in terms of both the collection of data and the subsequent analyses. However, some progress has been achieved due to the pioneering efforts of Paul Green and his associates during the last few years in the use of non-metric MDS in the context of market research problems. The techniques have been specifically applied in finding out the perceptual dimensions, and the spacing of stimuli along these dimensions, that people use in making judgments about the relative similarity of pairs of stimuli. 12. But, in the long run, the worth of MDS will be determined by the extent to which it advances the behavioral sciences. 13. 9. Robert Ferber, ed. Handbook of Marketing Research, p. 3-51, 10 Ibid. p. 3-52, 11 GB. Giles.